infinite sequences and series. Overview. While everyone knows how to add together two numbers, or even several, how to add together infinitely many numbers is not so clear. In this chapter, we study such questions, the subject of the theory of infinite series. Infinite series sometimes have a finite sum, as in, this sum is represented geometrically by the areas of the repeatedly halved unit square shown here. The areas of the small rectangles add together to give the area of the unit square which they fill. Adding together more and more terms gets us closer and closer to the total. Other infinite series do not have a finite sum, as with the sum of the first few terms gets larger and larger as we add more and more terms. Taking enough terms makes these sums larger than any pre-chosen constant. With some infinite series, such as the harmonic series, it is not obvious whether a finite sum exists. It is unclear whether adding more and more terms gets us closer to some sum or gives sums that grow without bound. As we develop the theory of infinite sequences and series, an important application gives a method of representing a function f of x as an infinite sum of powers of x. With this method, we can extend our knowledge of how to evaluate, differentiate, and integrate polynomials to a class of functions much more general than polynomials. We also investigate a method of representing a function as an infinite sum of sine and cosine functions. This method will yield a powerful tool to study functions. A sequence is a list of numbers in a given order. Each of a1, a2, and an represents a number. These are the terms of the sequence. For example, the sequence a1, a2, a3, a4, and an has first term, second term, and nth term. The integer n is called the index of an and indicates where an occurs in the list. We can think of the sequence as a function that sends 1 to a1, 2 to a2, 3 to a3, and in general sends the positive integer n to the nth term. This leads to the formal definition of a sequence.